All right, welcome. I get started here. So building a game is a lot of fun, right? You spend, months, if not years, iterating on this, crunching long hours, and finally get a product out there, and you go to launch it and get real users on it and expose it to the world. And there's still about, a 50-50 chance that the entire thing is just going to completely fall apart on you. Before coming to AWS, I was at PlayStation and witnessed some of this firsthand. Had a lot of launches that went well, thankfully, but some that didn't go so well, some like this. So this has become a pretty big problem in our industry overall. It's almost expected by players nowadays that a new game that comes out, and especially a console or AAA title, is going to be broken for the first couple weeks. And this is, a terrible experience for somebody that's spent $60 on a game. And similarly, in the mobile space, launching a game, you've got a free-to-play game, and your whole basis of success is getting a very wide adoption rate very early on, and then being able to monetize that. And if the initial release of your game is a whole bunch of one-star reviews saying, I can't even connect, this sucks, you're going to have very big challenges, and you have an uphill battle. So how do we actually solve this? How do we avoid falling into these same traps that have become so problematic? So what I'm going to do today is I'm going to walk you through this hypothetical game that I created, and it's just called Knights versus Samurai. I'm going to use this to illustrate the features that AWS has that can help you with your multiplayer game and how you can actually launch a game globally successfully. And this is actually some artwork courtesy of Dan Scott, who is a famous game artist, actually. Did a lot of World of Warcraft art back in the day, and he let me use this, so thanks, Dan. So the idea behind Knights versus Samurai is it's just going to be a no-frills deathmatch, 4v4, hack-and-slash chaos. You're running around, hacking your friends to pieces, and it's just going to be totally awesome, right? And this could be mobile, this could be console, doesn't matter. You can have a swipe, and you can slash your friends. It's just going to be awesome, cross-platform game. So with a game like this, low latency is going to be critical. Any kind of jitter or any kind of latency spikes in the network is really going to ruin the experience. If we're having our friend come right at us and we try to slash and all of a sudden he jumps and he's across on the other end of the map, it's totally going to ruin the experience. So latency is top of mind. Let's start by looking at that. This is a map of the average network latency within a region, courtesy of Superdata Research, and they're a game industry firm. The exact numbers aren't super important, but the takeaway from this graph is that if you're staying within a given region, say in a continent, like in North America, in Europe, in Latin America, and so forth, your latency numbers are pretty good. Anytime you have to cross a major boundary, like across the ocean to Tokyo or go from US to Europe, your latency jumps way up. Typically for a game like multiplayer game like Knights versus Samurai, you're targeting around 50 milliseconds latency. That's going to give you that best gameplay experience, and if you look across the board, FPSs, MMOs, et cetera, 50 milliseconds is kind of your golden number. So in order to get that kind of performance, we have to get game servers as close to players as possible. This creates a fundamental problem because we have a whole bunch of other stuff that we also want unified in order to give people a unified experience. We want people to actually have this global experience in our game. We want people to see maybe a global leaderboard to see how people are doing worldwide, see who's actually the best at this game. I want the opportunity, if I have a friend over in Tokyo, I want to be able to actually play him in certain areas. So we have a fundamental rub where we want to have a unified experience, but we have to have game servers as close to people as possible. So the naive approach to solving this would be to deploy servers worldwide and then deploy databases associated with each of those different servers where player data would be located. And then just connecting everything via a big replication ring. But the problem with that is that it adds 100+ milliseconds for each one of those hops. So if we have a truly global game, we can't just replicate the data everywhere, because if we want any kind of transactional integrity, like, hey, I killed you and I want to save it, then it actually has to make that whole loop back before you can give a response to the player. So anything that we just gained by putting our game servers close to our end users is now stripped right back away. So we can't do this. This is epic fail. It will not work. So what's the solution? How to be awesome, right? So what we're going to do is we're going to break apart our game into the pieces that really need low latency, that need that low latency game player experience, and those that don't. And we're going to put our game servers near players. So the ones that actually need low latency, we're going to locate those near players regionally throughout the world. And then everything else we're going to build as a set of HTTP APIs. Now, if you've been doing mobile development, this is probably obvious. This is a relatively new paradigm for multiplayer games as a whole. The idea being is that you're actually splitting apart the pieces of functionality that need low latency from the pieces that don't. So examples would be when you first log in, 150 milliseconds, 300 milliseconds for login is fine. Users expect that to take a second. We all benefit from the lowered expectations from how slow the web is, right? Taking half a second to log in, getting a little spinner is fine. But if you shoot somebody, you want that to be up to date. Like if you slash somebody, that needs to happen right then. So we're going to think on a feature-by-feature basis to actually split those two apart, and we're going to approach them differently. Any type of data replication is bad, okay? As I just highlighted, any kind of big replication ring is going to completely undo any benefits that we have by actually getting the servers near players, so we're not going to do that. But local caches of the data are good. Like having an actual local cache of your player data so that while you're actually playing, that data is locally available, and then when it's done, you can sync it back to your central stack, and I'll show you that in a minute. That's good because that gives you that performance optimization. Then the last thing I want to really focus on is just the concept that nobody really plays everywhere. This is one of those things that sounds good. Like, okay, we want to have this global game. We want everybody to be able to play everywhere. We want to have this global experience, but that's not actually like what happens, right? Like if I'm just playing Knights versus Samurai and I go in there and I say, okay, you know what? I want to join a game. Do I want the system really to automatically connect me down to a game server, in Brazil? Like, no, I don't want that, right? The latency is going to be terrible, and I don't even know how to swear in Portuguese, right? So, what you want actually is the vast majority of the time you want to be playing in your local region, and then in certain situations you want to make a choice, to go over and maybe join a specific friend, but that's very different, and it gives us a lot of advantages in terms of how we handle data than just replicating all the data everywhere just in case. Saying, okay, he's going to go over there now, he needs a bit of game data over there now, is very different, and it gives us a lot of flexibility in the implementation. So what's the best practice? The approach here is we're going to create a bunch of these separate pods. I think of them as like spaceship escape pods, like in Star Wars, the real first one where C-3PO and R2, they jump in and they're flying down, they're getting away from the Empire. The idea here is that these escape pods, they're all independent. Like they can all communicate to one another, but they're not dependent upon one another. That's a key differentiating point in the way we're going to architect these. We're going to create them so if any one of them explodes, so if something happens in Tokyo, if something happens in Frankfurt, it's going to take down that set of players, but the rest of our worldwide game is going to continue as if nothing happened. So as players come into the game then, what they're going to do is they're going to first communicate with our HTTP stack. They're going to come in and say, okay, I need to log in. I need to get my friends list. And they're going to make a call to the HTTP stack. And you might have just one central one of these, depending on your game, or you might have more. But it's not uncommon to actually just have one of these at one place in the world. So if you're running a game that has players in the US and Europe, you could easily just have one set of login servers that has your data, has your core data, located in Virginia on our East Coast. And then you could have game servers located in Frankfurt, maybe in Dublin as well, located in the West Coast US, so that when people are actually doing their multiplayer, they're using maybe UDP, maybe they're using WebSockets, but then their actual data segment is all going back to that central API stack. So digging into one of these, what does the actual API, this HTTP layer, look like? So this is an example, and this is kind of AWS, Core 101, whatever you want to call it. You can find this on our website through a bunch of different use cases. But this is a lot of, web stacks look like this, but it's a great architecture for that central game stack. And basically what we have here is we have an auto-scaling group. We're running web services on a fleet of EC2 instances. We're able to scale that group up automatically. We set up some criteria and say, okay, when CPU jumps up too high, scale up more servers. When CPU usage drops back down, get rid of servers, pay less. And then we're using S3 and CloudFront to distribute any of our static assets. So think about the case where a person actually, they come in the game, and they want to log in, they want to get the latest map pack. Basically, what would happen is they would make an HTTP request, they would log in, that request would go down through your web stack, it would access our database layer, I'll come back to that in a second, and then it would indicate, okay, you have a new piece of data that's available, pull that data down from S3, and route it through CloudFront, which is our CDN. The configuration there is straightforward. You just set up a CloudFront distribution, you point it to an S3 bucket, and then you get a URL back. So you configure your app and say, okay, you come in, is there any new content available? Yes, actually, here's the new map pack, and here's the URL. Then the client makes a request to CloudFront, hence S3, pulls that down locally, and now you have the content unpacked on your local device. And I have DynamoDB here at the bottom as our database. I want to spend a minute and just talk about that. You know, a lot of game companies, when they're starting out, end up using MySQL because it's familiar, it's easy to get started. You can certainly use MySQL with us. We've had quite a few game companies move from MySQL to DynamoDB, and we very much encourage you to look at DynamoDB. It's our fully managed NoSQL solution. EA this past year at reInvent actually talked about how they replaced 120 different MySQL shards with a set of DynamoDB tables, and they dropped their storage costs. I think they said 90%, and their scalability went way up. The thing about DynamoDB that's great from a game developer perspective is it's fully managed. You don't have to worry about game servers. And by and large, most game data is key value based. And that's the differentiation between DynamoDB and something like MySQL or RDS. You know, MySQL is going to give you more richer, you know, complex joins and queries, but that's not really what you want with games, right? You're writing a whole bunch of little tiny data, like just completed this level, just got this item. So you're doing all these, you know, very fast atomic increments and updates, and that's what DynamoDB is best suited for. So DynamoDB in this stack, very, you know, highly recommend you take a look at that. Very popular choice. And then for anything where you're actually processing data that doesn't need to be processed right now, putting that into an SQS queue and processing that later. So example, I upload maybe a custom avatar, and then as part of that process, that avatar needs to have some thumbnails generated or some other piece of metadata needed to be updated. So when you actually upload that avatar image, rather, sorry, then you would post that up through your stack, but then put a note into SQS, say, okay, by the way, Nate just uploaded a new avatar, and here is the actual ID, and go ahead and resize it, and then spit out a bunch of thumbnails in S3. And a couple other pieces I want to highlight that are pretty recent additions here. So if you're on mobile, Cognito is a great service that is very popular with mobile developers because it handles all of your unified identity. And you can use it in conjunction with this web backend that you build out for your core API services. Essentially, Cognito allows you to associate, you know, Facebook, Google, you know, other social logins, your own custom logins with a single unified Cognito identity, and then you can use that identity within AWS to access other AWS resources such as S3 buckets, et cetera. So it's a great way to pull that together, especially if you want to use any kind of social login. Also supports custom logins, so if you have your own login system, you can integrate that with Cognito. It just gets rid of all of the stuff that you have to worry about around security and authentication, authorization groups. You know, service highly recommend if you're on mobile platform. And then last but certainly not least, in terms of things you can do in the background, maybe you send an SNS mobile push notification. I update my score, I defeat somebody, I jump over them in the leaderboard, send out an SNS, say, hey, Nate just beat you, better get back in the game and go beat him. So let's walk through what a game flow actually looks like. And this is just another way to look at what I mentioned already. Player logs in from their mobile device via HTTP or their console, PC, what have you. Download the game assets, as I mentioned. Then they want to do some kind of matchmaking, and here's where the multiplayer servers come into play. So I get my latest map. I say, okay, I'm ready. I want to go play 2v2 or 4v4. I want, you know, this certain mode or et cetera. And it says, you're in luck. Here's a game server over here. And then I'm going to directly connect the game client to that actual server. I'm going to proceed, hack apart my friends, hack and slash, and then at the end of it, at the end of the game or the end of the match, send the data back to that central server. Now, since we've designed that central stack as a set of API services, even though this shows the game client is actually sending that in, you don't have to send that data from the game client. You don't have to trust the game client. Remember, that's just an API endpoint. You can secure it to talk through a number of different devices, whether or not it be end users, or you can also have your game servers actually contact it, right? Because it's just an HTTP API. So if you have your game server and it's authoritative, you could have your game server just post to that same API endpoint and update your data that way. Again, that's one of the big advantages to approaching your game in this service-oriented architecture, is you can split apart these HTTP services. It's not necessarily just one big monolithic stack. You can have HTTP services for login, you can have a service for matchmaking, you can have a service for leaderboards, and split these all apart and scale them independently. Now switch gears here, and I'm going to look at now, let's look at what the actual multiplayer game server pieces look like, because these look a little bit different. So these are different because there's not a load balancer in front of them. These aren't HTTP. These are going to have long-running connections. So what we're going to actually do is we have these out there, and they're going to be publicly accessible. So using AWS, using our VPC, which is our virtual private cloud, you can actually define subnets. And on a subnet by subnet basis, you can determine whether or not they're public or private. In this case, we've decided, OK, these are going to be public, and these are going to be the actual game servers that are available for users. And then in the private subnet, we're going to have our local cache that has our local player data. And then the other thing that we're probably going to want is some kind of low latency message bus. And what this enables us to do is have our game servers actually communicate to one another. Your game may not need this, but many games do, because they maybe want to do chat across players that are on different servers. Like I log into server A, and we're playing together, and then another one of my friends logs into server B, and I still want to send them a chat message even if I'm not directly connected to that server. The way that would happen in this case is I would actually send that chat message to the server, and then it would route through that message bus. And this example shows RabbitMQ to send it to my buddy, and he would then receive it on the other server. RabbitMQ is one of the most popular one of the most popular processes for this actual usage, and I'll go into a little more detail here in a second. But highlight a few things. And these slides are going to be made available, and we're also actually recording the session. But highlight a few things here, which is just the C3 and C4 instances are the ones you want to choose. We have a whole bunch of instance families that you can choose for EC2 instances these days. Some of them are more optimized. They have more memory. Some of them are more optimized, like the C series, that they have more CPU. The C3 series in particular is great bang for buck when it comes to high-performance CPU and also very high-performance networking. It has our enhanced networking capability. So as a game developer for basically your whole stack, whether or not you're talking about your multiplayer pieces or if you're talking about your HTTP pieces, definitely look at the C3 instance. And it's got a variety of sizes, large, extra large, et cetera. I'm going to skim over this, but the big benefit of enhanced networking is hardware virtualized networking. So it basically means that you get hardware-type performance of your actual network driver. So before the enhanced networking, everything had to be handled by the hypervisor. Now it's actually handled down in virtual functions actually on the device. Going back to RabbitMQ, which I mentioned was the piece for that multiplayer servers communicating together. So this is what a RabbitMQ deployment would look like. You would have a private subnet. You would spin up 2 different nodes, and then you would put a load balancer in front of them. And on this slide, I have to skim through a little bit of this just for time, unfortunately, but these slides will be made available. These links will walk you through it. If you'd like to talk more about RabbitMQ or the need for it, feel free to grab me after this. And then finally, I'll just show you a RabbitMQ config that you can use out of the box. And one other option that I'll just highlight for that layer for interconnecting your game servers, if you're using Redis for other pieces of your app, and I skimmed over that a little bit, in terms of caching, we have Elasticache, which supports both Memcache and Redis. Memcache is very familiar. It's been around for many years. Redis is very popular with game companies, though, because it has more advanced data structures. You can do stuff like in-memory sorts for leaderboards. You can do sets, which means you can guarantee uniqueness of a person in a given set. So if you want to say, oh, here's a set for a given game, you can use a set for that in Redis, and it's all in memory very fast. So Redis is the dominant version of Elasticache that's used for games. If you're using Redis for other pieces of your game, you can actually use Redis PubSub rather than RabbitMQ. So it's another option, same use case, idea being you would have all of your game servers subscribe to this common PubSub channel, whether or not you're using Redis or whether or not you're using RabbitMQ. This common channel then lets you route messages between different game servers and give that more unified chat experience. And how do you actually then configure this? So the combination of CloudFormation and Chef is what we see to be very successful with game companies. And what CloudFormation is, it's our service for actually describing your EC2 instances. So once you actually spin up your EC2 instances and all your other AWS resources, you can then create a template out of that. It's just a JSON template using CloudFormation. You can say, OK, I want to create a template out of this. And then you can use that template to replicate those AWS resources either in the same region or in other regions. And so that'll handle all the creation of your actual AWS resources. It won't necessarily handle things like actually spinning up game servers, for example. And for that, or for configuring RabbitMQ, that's where Chef comes in. And what Chef is a configuration framework, if you're not familiar with it. It just runs. It's a Linux-based. There's also Windows support for it now. It's a Ruby-based description language, DSL, and you just define resources and say, OK, here's a group. Here's this piece of software. Here's how I'd like it configured. And then it runs through and takes care of actually configuring those. And so to illustrate this, we actually put together a template. And unfortunately, I don't have time to walk through the demo. But the demo is similar to what I'm going to show you here. That actually uses CloudFormation and Chef together to spin up an Unreal Engine game server in a configuration similar to what I was just showing. And this is something we're going to be making available on GitHub very soon. So keep an eye out for it. It's something you'll be able to download and just put in your AWS account and spin up a game server. The basic process here, and again, we'll have this documented and show this on GitHub, is you just fire up the CloudFormation template. You give it a bunch of parameters, like here's the description, the JSON file, and then here's actually the region I want it in, and then here's the name of the zip file with the Unreal Engine. And then when you actually launch that command, it's going to spin up EC2 instances in the background, and it'll give you a status dashboard like this in the AWS console that'll show you the status, saying, OK, spinning up these different servers. And when you're all done then, you're going to wind up with a completion diagram like this. And if you look in the upper right, it has a public IP address. That public IP address is then what you could actually connect your Unreal client to. And if you log into that, you'll see the Unreal Engine server actually running in the background at the bottom. So last thing I'm going to highlight is server registration. Then I'm going to turn it over to James Gortzman, who's the CEO of PlayFab. And what they've done is they actually built out a platform as a service game hosting offering following basically these same best practices that we talked about so far. So he's going to give you a real-world example of how this works for the game Loadout, which is a popular Steam game. So the last part we have to think about is how do we actually know where the servers are? So we've already covered, OK, we've got this central stack. Great, we've got all these service pieces, the service-oriented architecture. You log in. I want to be match-made to a server. How do I actually know where that server is? Where my server's at, right? Sorry for the bad pun. Couldn't resist. Concept here is straightforward. The idea is as we have game servers spinning up, we want them to register with that HTTP stack that we already talked about. And when that server comes up then, it's essentially going to send a health check to our API stack and say, OK, I'm a new game server. Maybe I have these modes available. I'm in this region. I'm in Frankfurt, et cetera. And the central API stack then is going to put an entry in its DynamoDB table and say, OK, now I have you listed as another game server that people can connect to and play. So when that game server spins up, for example, in Tokyo, it's just going to send an HTTP request. Maybe it sends it every 30 or 60 seconds. It's up to you. But it's just going to hit that API and just say, hey, I'm here. Here's my IP address, and maybe a couple other pieces of information that are useful, like I have this many players connected to me. And then you rinse repeat as you add other regions. And so if you follow this process, it actually is pretty simple to spin up new regions. And a new region is just a matter of taking that CloudFormation template, spinning that up, in, say, South America or Frankfurt or wherever you want a new game server, and then having that IP address and just registering that new server with your central matchmaking service. And when a player comes in, then they're going to have that service available to them to play. And then periodically, you're going to have a background worker that's just monitoring the health of those. It's doing some cleanup. Basically, it's going to look at that table, and it's going to say, OK, when was the last time I heard from all these servers? Is there anyone maybe that I haven't heard from in a while? Maybe the last time I got an update was 30 minutes ago, so it seems like that server is unhealthy. I don't want to send people to that server anymore. And then it can just make a simple call out to an EC2 API to just say, OK, terminate this server, and then remove it from the DynamoDB table. So pretty straightforward process. If you put this in place, you can have just a very simple, few dozen line of code that just receives a registration from an actual server, puts that entry in DynamoDB, and that really is all you have to do in terms of matchmaking. Then you have your list of your servers, and when a person comes in, you just match him to what's available on the table, give him a server, and he can go hack and slash his friends, right? Just some details to think about in terms of security. And again, these slides will be available, but one of the things I highlighted is putting an HMAC in there, which is just signing the actual request. And we have examples of that in our documentation as well. And I'm going to skip over these, but feel free to grab me. This is actually very similar to the analytics talk I gave in the past hour, which is just collecting all those logs off of your actual game servers to do analytics on them. You can not only collect them through S3, but you also have the ability to actually stream those to Kinesis, which then you can dump to S3 or another bucket. And if you're interested in this, about collecting logs, getting player data from your actual game servers, please do grab me after this. Glad to talk about it. And the last thing I'll just point out here is we actually have an adapter for FluentD, which is very popular open source, that'll go through Kinesis, which is our managed data transport service. And then from Kinesis, you can dump your data into multiple different places, be it S3, which is great long-term source, simple storage service, or Redshift for doing some additional analysis. Wrapping up here, and then I'm going to hand it over to James. Just want to highlight, there's a set of challenges as you go broader, right? And China in particular is one of them because of the fact that network connectivity from mainland China to outside of China, has certain challenges. So the benefit of following this approach where you have these pods is you can then replicate it. And I want to just show one good example of how you can make a global experience even for China users while still overcoming any kind of network latency or other issues. So on the right side, what we have here is we have this pod that we've built out where it has our central auth and it has our game servers located around the world. And then for China, what we're doing is we're actually deploying another. It's a separate set of auth servers and it's a separate set of game servers, and we're going to actually deploy that into the AWS China region. And we're going to do that because we're going to need those to actually be within China so we get the right network performance. But we can still actually have a unified game experience if we follow this service-oriented architecture, because now we can have a global leaderboard service that lives in one of our other regions. And because it's not time-dependent, because it's not latency-dependent, we can still have game clients or servers posting to that service. And so we can still have the illusion to an end user. They can still think, hey, I'm playing a global game. I can see people on my leaderboard against, from China. They still get that, kind of feeling of a global connected experience without you having to create this huge data replication or directly connect all this stuff in a means that can be very fragile and cause other issues for your game. So with that, I'm going to turn it over to James, who's going to walk through some of the real-world architecture that they have for PlayFab. I think there's a mic on the table there. Yeah, cool.
Hello. So what's crazy about this talk is that when Nate and I first put this together, we didn't do a lot of coordination between our slides. He made his slides, I made my slides, and then only a day or two before we gave the presentation, we kind of merged the slide decks. And what's crazy is the best practices that Nate just described are like exactly the architecture that we built out. So either we're both crazy or there's something really smart going here, because two completely independent companies came up with a very literally identical set of best practices. And so everything you just heard Nate talk about in terms of how he recommends you build out the services and build out high availability multiplayer gaming is exactly what we've done at PlayFab. And so we built this architecture over the past actually few years, and we're going to talk today about exactly how we've used this for a game loadout that's being hosted today on PlayFab. And we'll talk about some very specific tips and tricks and best practices we've learned operating on top of Amazon. So I get to give like a 30-second kind of explanation of what PlayFab even is before I kind of dive in and explain what we're doing. So we are a sort of back-end as a service for games that has already built out a lot of the architecture you just heard about. And so the basic idea here is if you're building a game and you want to have multiplayer servers and you want to have high availability and you want to have live connected services and events and all this other great stuff, but you don't actually want to write a lot of server code, we've kind of done all that for you. And it's all available through a set of APIs that has some core services. It's got a whole sort of dashboard and set of tools available. And finally, we've sort of pre-integrated with this ecosystem of a lot of other companies out there, including Amazon, Facebook, Google, iOS, and so forth. So that's sort of that's who we are. One of the games that is hosted on PlayFab is a game called Loadout. It's built by Edge of Reality down in Austin, Texas. Some of you may have heard of it or even played it. This game was originally started, actually, so PlayFab is known as PlayFab today. We started out originally as the internal architecture for Uber Entertainment, a game studio in Seattle. And back then it was called UberNet. So if you play Loadout, you actually will still see references to UberNet. But we've taken that UberNet kind of proprietary internal platform and sort of cleaned it up and repackaged it as a service for third parties called PlayFab, and you're welcome to check that out. So some stats just to give you a sense of this kind of scalability we've seen. So the game first launched early last year, January 2014. Since we launched the game, we've had actually well past 1 billion API calls now processed by the game. At the peak in February, the game had several 100,000 DAUs. We had 120 servers around the world handling the multiplayer game sessions. This is a typical free-to-play first-person shooter game. So exactly the kind of pattern that Nate just described, where you have a bunch of game servers around the world, a central set of matchmaking services. Players would connect, enter a lobby, find a match, get assigned to a game server, and then route it off or hand it off to a game server somewhere in the world. They would compete in a match on that game server, competing against 16 different players, battling it out. And then when the match is over, they'd get sent back to the master lobby, and a bunch of stats and scores and so forth would be sent back to the kind of headquarters services to be recorded for future use. The game was, at launch, we had some dedicated servers that we had leased from some third-party hosting services, but we had not expected the kind of load we were going to see at launch. And so our system auto-scaled at launch and spun up a ton of EC2 instances to handle the overflow. And that's actually a really nice pattern. EC2 is a fantastic service. Some of you sometimes may want to have your own dedicated leased hardware boxes around the world, maybe in your own data center, maybe others. What's great about EC2 is it's so quick to spin up a new instance, it's an amazing way to handle your overflow. So if you have a set of fixed boxes and suddenly load surges, you can automatically spin up into EC2 instances to handle that additional load, register them in the right processes, then as your load starts to go down again, you can shut them down and clean up. And so that's actually the pattern we followed at launch. We had 120 fixed servers and 110 EC2 instances set up. So some core architecture instances, we designed the system to have no scheduled downtime, auto-scaling, backend changes should be invisible to developers, and we wanted buffering in there so that if there are surges in load, things wouldn't get dropped on the floor. So to give you a sense of the basic architecture exactly, we're following exactly the pattern Nate described. Clients would come in through, so clients running our games, we had an API that the game clients would be authored against. Going in through Route 53, every game on our platform has a different API endpoint. That's how we keep track of which games are which, but they're all ultimately getting funneled through the same endpoint into the same set of web servers. Those web servers are being balanced via ELB, Elastic Load Balancing. Those web servers are handling those API requests coming in. And then we're using the whole gamut of Amazon services, S3, DynamoDB, and others. And we've been using Amazon Redshift for handling all of our analytics and back-end BI reporting. So once you have, and then for the actual multiplayer, again, same model. We've got a bunch of dedicated game servers around the world in different data centers, and we have a whole set of matchmaking services set up to route and hand off players to the appropriate servers around the world. Just to give you a sense, this is an example of the kind of web APIs that we're providing as a PlayFab service. These are all hosted on web services. If you're building a game for yourself, or if you're building your own back-end servers yourself, your APIs are probably going to look something similar like this. You're going to want to have APIs for authentication, APIs for logging in, APIs for storing and retrieving player properties, APIs for managing friends lists, APIs for the matchmaking. This is a pretty standard set of APIs. And we, just like Nate was describing, we actually have different APIs for client versus server, because clients are inherently non-trustworthy. We don't trust clients to do things like, say, give me 10,000 gold coins, or give me the sword. Only, what we do trust a client to do, say things like, I just bought the sword, or I just killed a monster, and then the server API is trusted to do things like give the player this sword or give the player this gold, because it's much harder to hack the code running on a server. So an example of a web API call on the left is what it looks like coming in. So the client might make a request, something like going to a given API, matchmake, passing in some parameters. The web server in the background does all the work, figures out who to matchmake against. The response comes back saying, great, you've now been assigned to lobby 32 running on this IP address with this host name. Here's your ticket. Go off and make that connection. So that might be what the round trip would look like. Some tips and tricks now. We are using Elastic Load Balancer logging for all of our title tracking. So every request coming through ELB can kick out logs. Those logs are being dumped into S3. And then from S3, we're actually taking those, analyzing them, and eventually shoving them off into Redshift ultimately for all the stats tracking. So we're able to give all of our customers a very detailed breakdown of every API call they're making, what the performance of that API looks like, what the throughput looks like, and it's also useful for us as well to know who's doing what on a system, all coming through logs, being kicked off by ELB, which is great. So here's what a sample usage report looks like. On the left, you see the various API names, and we have a lot of information on how many times the API is being called with what performance characteristics. And again, those are all logs being generated out of ELB, which is cool. Another pattern we're using, the whole singleton pattern. So we've got things like the matchmaker, where you actually want to have a singleton server that you want to have a singleton server that is able to kind of know all the different servers out there and make the requests appropriately. If that server ever falls over, though, you're kind of dead because it's a potentially single point of failure. So what we're doing here is we actually have an auto-scaling group set up using Elastic Beanstalk, such that if a server ever goes down, it can automatically do a health check, determine the server's down. Amazon S3 will then, Route 50 will route all the traffic over to the server that's still working. We'll then take down the server that's bad and set up a new server. So we'll detect that failure automatically. Tools we use ourselves, we're big fans of both VictorOps and Pingdom. We use Pingdom just for kind of continual, it's almost like we have a bunch of checks in place, including CloudWatch and others, but we also use Pingdom for sort of a backup to make sure everything's running. We use VictorOps for notifying our DevOps team when there's problems and outages. We have a whole bunch of alarms set up. We have another great pattern is this notion of buffering. So in our case, one thing that often happens when you have a lot of traffic is you get a huge surge in event traffic. And if you're getting a big pile of events being generated, you don't want to drop any of those on the floor. And so we always write events to local hard drives, local drives or disks on the various boxes, and they can sit there for as long as they need to. It could be 1 minute, could be 20 minutes, and then eventually we have a process that goes around, picks up the logs, processes them, and throws them into Redshift. And that kind of what you don't want to do is have your web servers directly writing into Redshift or directly writing into a central stats database. It might seem like a clever thing to do, but there's no buffer in there. And then what happens is if you suddenly get a sort of ton of load and you can't keep up with Redshift, things start to slow down and you can get cascading failures, which is really a bad thing. You don't want that. We're using DynamoDB. Just like Nate was saying, we're big fans of DynamoDB. We use DynamoDB for almost all the key value storage in our system. We also use RDS for some other relational database services for certain other things. And in fact, even things like stats and currency now, we're in the process of moving over to DynamoDB because DynamoDB's added some recent features to make it a really good replacement even for traditional RDSs. So that's some things of where we're storing data, some examples of the tables. I'm happy to chat afterwards. We have multiple tables set up, and we're able to use various range keys to help us with indexing and retrieving data in different ways. One thing we learned a lot about is the value of having multiple availability zones. We've got multiple deployments. One trick is if you do have multiple kind of centers, for example, Oregon versus Northern California, one pattern that's actually kind of nice is to actually have in your code things like a player object, for example. The player object is smart enough to know which server, basically knows which players in which regions. And so if it's going against a given region and that's actually not where the player is stored, it's smart enough to route off and go get the player's record from another region. And so this is a pattern that we use to move player records. I mean, you don't want a player ever living authoritatively in more than one place because then you can get conflicts. So you always want your players in one place or another, but you can use patterns like this one to allow you to, on the fly, move players around the world in terms of where their central identity is stored for performance reasons. And with that, we're basically out of time, so this is it's great to build tools for yourself so that once you've got your whole game up and running, you're going to want to have tools so you can go in there and actually manage and analyze and see what's going on. I don't have time today to give you a demo of this, but you're welcome to check it out at playfab.com. And so with that, I think that's basically, that's it. So thank you very much, and appreciate your time today.